So you should have heard the message, so not recording anyone behind the back. So thank you very much to, first of all, to Professor Kevin Lano to join us and agree to give this presentation. But thank you also to all the participants for joining us for the third season of the virtual meetup. This time we took a slightly longer summer break because of Meetup that was held last week in Aachen. And but here we are with a strong program, and we are going to start the season with a very interesting topic. So we have Professor Kevin Lano from the King's College giving us this presentation. He's been working with software languages for over 30 years. He has worked on the Z++ extension of the Z language and worked on the semantic of UML, OCL, and the model transformation languages. So quite a strong background, and he's now leading a research team with 3 research assistants and 5 PhD students at King's College, where, by the way, the MDNet initiative was started. So we can see that the King's College is a stronghold for MD. Today, Professor Lano is going to talk about a presentation that is connected to a topic very important for us at Strumenta, that is language transformation, program translation using model-driven engineering techniques. And well, if you have attended other presentation in the virtual meetup, I don't need to convince you of the importance of this problem. So dealing with legacy modernization and in a way save the value that is trapped in large application written in a language that happen to be legacy. And by the way, I think it's the destiny of every valuable system that keep being valuable for a sufficiently long time, right? And in particular, if I understand correctly, these techniques that we are going to see today are based on reverse engineering and derive UML and OCL models, and then forward engineering from there. And I hope I represented the idea correctly enough.
Yeah. That's right. Yeah. Okay.
So now I can shut up and let Professor Lano take over. Thank you very much.
Thanks. This was a paper that was presented at ICSI as a short paper earlier this year. So this is an expansion of that presentation and an update. So as Rodrigo has said, it's a major problem, legacy software. There's many systems out there which are doing critical things, business critical, financially critical, or just in terms of government and other organizations, which were written potentially many years ago, but they're still depended on. And the maintenance of those systems can become very expensive because, for example, in this first case, COVID, impairment of COVID measures because of legacy software that involved some legacy COBOL software, and there was a lack of engineers who could deal with that software, and so these measures, the economic measures, were delayed. Banks, of course, are one of the major organizations that depend on legacy software. They also have lots of money, but it still is a major commitment of resources for these organizations to modernize their software. So reverse engineering, well, has been mentioned for many years. In fact, I started my career in computing at Oxford University in the 1990s, or even 1980s. At the end of the 1980s, I was at Oxford University working on a European Esprit project with various European partners to do reverse engineering of COBOL and Fortran. And so that was 30 plus years ago, and we're still talking about it now. What perhaps has changed in the last few years is that there have been various efforts at doing program translation using techniques that are adapted from machine translation of human languages. So there's been various neural network and other kinds of machine learning applied to program translation. Now, I'll come to some of the issues with that later on, but what I'm doing is somewhat different, and in fact goes back perhaps to the original idea of reverse engineering, which was to take existing software and produce a specification. Now, the question is, what is that specification going to be in? It should ideally be in a form which can be translated to a number of different targets. So this specification notation here has to be something which is fairly universal. It shouldn't really be a specialized and customized notation, because then it itself becomes a legacy problem. It might only be supported by one organization, and then that the specifications from the legacy software themselves become unusable. So my choice here of the specification notation was essentially the UML and OCL, which are international standards, and there's already a great deal of software that supports them. And more importantly, perhaps even, there's a lot of software which does the forward engineering. And so this forward engineering part from a specification to a modernized platform, to a large degree, there's already the software and the toolkits which do that for you. So my focus has been on the reverse engineering step to accurately capture the semantics of software in programs, in source code, and translate that to UML and OCL. Now, another issue that comes about with language translation is that if you're translating N source languages to M target languages, then you need N times M translations. And of course, that rapidly becomes infeasible. So we find there are various online tools and even some commercial offers which are rule-based. So they have a fixed set of rules for doing a translation from language 1 to language 2. They might do, for example, Python to JavaScript or JavaScript to Python. There are tools which do that. But they have to do that for each, they have to create a set of rules for each pair of languages. And of course, that, as I say, becomes infeasible in terms of number of translations needed. So using an intermediate language makes sense also from this standpoint, that the number of translations or abstractions doesn't increase in a quadratic fashion, it only increases in a linear fashion with the number of languages involved. So what does it involve? Well, it involves the abstraction. This is the key thing here, the abstraction of the source program into a UML OCL specification, which as far as possible captures precise semantics. Now, a lot of the languages out there, of course, the programming languages that we might want to translate, they don't have a precise semantics, or they might have various variations. So if you look at a C program, obviously the semantics of a C program will vary depending on which machine it's executing on and you know, which processor is being used and so on and so on. There are various things which are defined by the C language standard, but as you go further back in time, perhaps then those standards also become less precise. So I say we can capture the precise semantics. We can certainly capture some semantics, but in certain cases, for example, floating point arithmetic or something that can be machine dependent, then there has to be some assumptions made by the person doing the reverse engineering, and obviously we need to do some testing when we do the translation as well. And then the forward engineering, as I say, can be done often by existing MDE tool sets, like Papyrus, which is a well-known tool set, and there are various others. Now, I've looked at 4 languages so far, 4 source languages. C, as defined by Koenig and Ritchie, Java version 6 and 7, and JavaScript and VB6. Now, the actual parsing of those languages is done by the ANTLR grammars. The ANTLR parser are using ANTLR grammars for those languages. Why ANTLR? Well, it's an established tool. It's got a very large number of existing grammars for programming languages. Pretty much all of the main 3GLs anyway are supported by ANTLR. And it also has very few technological dependencies. It only depends really on Java. So it's a simple tool to use. Now that produces syntax trees. And one of the novel features of this approach, really a key to the approach, is a language that I've called CSTL, Concrete Syntax Transformation Language. And what that does is it has a series of rules for rewriting abstract syntax trees, rewriting them into text, and it performs various kinds of text substitution, transformations. It's a simplified language that's dedicated to processing syntax trees. That then is used to define the abstraction transformation. So those abstraction transformations are written in this kind of scripting language. And they produce UML OCL text, which can then be forward engineered into a variety of language. My own Agile UML toolset has 7 different targets. Another thing that's needed here is a set of libraries in the OCL language to support features that occur in programming languages like exceptions, iterators, and files, and so on, to support those features because they're not in the existing OCL definition. So essentially this abstraction is in terms, the abstracted specification is written in terms of these libraries. And then implementations of those libraries have to be defined for the different target languages. But essentially, this is a standard API for working with files, for working with sockets, for example, all of the things that you might do in a programming language. Well, not all of the things, but lots of the things you might do in a programming language. So you get a standard API. Once you've abstracted these codes, then they're all using the same API, regardless of the source language. Okay, so the ANTLR parser is used to produce a target. It's used to produce a syntax tree from a source language text, and then that's input to the CSTL script, which produces the UML OCL. So the CSTL script is doing the real substance of the abstraction to a specification. These are pretty much standard OCL UML with some additions, mainly isolated in libraries that are not present in standard OCL. And then we can forward engineer. Let's have a look at some examples. Here's what the CSTL looks like. So if I'm going from Java, one of the rules in ANTLR, in the ANTLR parser for Java 6, 7, is expression. So this covers all forms of expression in Java. And we have a corresponding rule in CSTL. That rule takes a tree which has 1, 2, 3, 4, 5 terms in that tree. It's a tree expression. It's an expression tagged tree with 5 subterms, and these 5 subterms occur like this. There's 3 variable parts that vary between different expressions, and we've got a question mark and a colon, and that's obviously that's going to match against conditional expressions in Java, and the translation is a conditional expression in OCL, naturally enough. Well, this looks simple, but it is a bit subtle, because here the _1, the _2, they represent arbitrary AST subterms. They could be any subterm that's going to occur in a tree of this form. On the left-hand side, it's the source tree. On the right-hand side, it's the translation of that source tree. So here it's a recursive application, essentially. It's saying translate something of this form, a tree with these 5 subterms with this form, into a bit of text where the translations are applied recursively to the subtrees. Likewise here, casting, and we get a corresponding cast in the target, and instance of becomes this. Statements in a similar way. Conditional statements become conditional statements. For loops become for loops, and so on. For Java, it's not really so difficult, but for C, then actually, the translation is a bit more complicated. The types, extension types and libraries, well, some of these extensions are quite well known and understood, like function types and map types. These have been talked about by researchers in the OCL world for a long time. The Eclipse OCL already has map types. To represent languages like C that have got pointers, we actually need a reference type. Other things, dates, byte processing, bitwise operators, reflection, exceptions, iterators. Iterators can not only represent the normal kind of iterators you might have, but they represent things like generator functions in JavaScript, and database result sets that you might get from SQL queries. OCL file, processes for threads, and data source for data sources, sockets, HTTP. Well, issues. One of the major conflicts between a programming language and OCL UML is that programming languages tend to use side effects, and this is a big obstacle to semantic analysis of programming languages, of course, and it considerably complicates semantic representation. Essentially, what you have to do is separate the pre-post side effects, pull them out of a side effecting expression, and separate them from the actual pure query semantics of the expression. So potentially the size of the representation can be significantly larger than the original code. In languages like Java, there are literally hundreds or perhaps even thousands of libraries, likewise in Python. So only the core language features can really be represented, the main libraries that are most frequently used. Some of the more specialized libraries, the translator, the person doing the abstraction would have to define their own rules for doing that. Another real problem is unstructured control flow, like gotos and it's switched in some languages. These, where possible, are replaced by structured versions. At the moment, I'm not translating GUI code. Now, we've done quite a lot of work on these 4 source languages, and the actual abstraction scripts themselves are not very big. So the largest is this Java abstraction to UML. It's about 3,000 lines of the CSTL language, and it took about 5 months of effort. So these are quite compact, they're quite concise things. Now, in terms of grammar coverage, one measure of that would be the number of grammar rules in the ANTLR parser which have been dealt with. And generally, the coverage is quite high in those terms. You can also ask about library coverage for C. Of the 179 operators in operations in Koenig and Ritchie, we've got 88% of them, and so on. So generally quite good coverage, but not complete coverage, but good coverage. Now, what's important, especially for critical business uses, is that the functional equivalence of a source and a target. So we did quite a lot of work in the finance industry, and there's the great concern that the functionality of the source and target are the same. And so we're really interested in evaluating the translation based on the functional agreement between the source and the target, and this is evaluated by testing. This is called computational accuracy, and the Facebook Meta group who've been working on their transcoder tool, they've also used the same measure. So you apply a set of tests to the source program and to the target program, and effectively evaluate the percentage which are the same. So we used about 100 cases in each of these languages to do that evaluation. And we come up with this table. So some of these translations are missing, as you can see. I've only done a certain number of these. But generally the translation accuracy is quite good.
A quick question on the testing part. Is it okay if I ask now? Or
yeah, sure, yeah.
So on the previous slide, for measurement of accuracy, as part of the translation and reverse engineering, are there steps which define data sufficiency requirements in terms of if I have to reach test coverage of, let's say, 80%, what are the data requirements? Does it come from reverse engineering, or since it is functional test only, whatever is available in, let's say, pre-prod, we can use it for testing?
The tests were manually constructed in this case, based on the source program. But in principle, we could actually generate test cases from the specification using model-based testing. That would probably be more systematic. So having got the specification, having got the specification in UML, we could actually generate test cases from that specification, and then apply them to the source and target. We've got someone working on model-based testing where you can just, from the UML model, generate test cases. Yeah, that would probably be a more systematic approach. At the moment, basically, I've done what Facebook did with transcoder, which is to manually create tests with the intention of having coverage, obviously of the interesting functionality of the system, but there's no claim that those have a particular coverage.
Got it. Thank you.
Thank you to others to ask our first question in this season. And I forgot to tell that if you want to ask questions, you can just unmute yourself, or if you prefer to write them, you can write them in the chat, and we'll interrupt our speaker and try to find the good moment to ask them. So you have the two options.
Federico, since you've invited questions, I have a question. Professor Lano, this is really fascinating. I can't do what anybody on this call can do, as Federico knows. I'm an implementer and more of a product manager for our transpilers. But I have a question about, so far the discussion has focused on individual operators, language elements, functional statements. And as an implementer who's done a lot of these kinds of projects, I've started to look a little bit upward at more at the level of a design pattern. So if you take 5 or 6 functions, operators, statements in a combination, or even larger, say somebody the other day used the term a paragraph of code, which kind of made sense to me as a good metaphor. Have you found in your experience that if you get the individual transpilation or the individual transcoding conversion done properly, then it will generally also hold as you step up to the level of an entire design pattern, or say an entire paragraph of code?
Yes, I think that would be almost the next step, is to try and recognize these larger patterns and well, code idioms or code design patterns. And indeed, I take advantage of that in some respects with C, because you know, pointer manipulation in C, I'm effectively assuming that it's being used like an iterator, let's say, you know, pointer addition, subtraction. If they're doing that, I'm assuming, well, okay, this is an iterator, and I can translate it that way. Obviously, they could be doing something really bizarre there, but this would be a very useful thing to do that systematically. I think once you get to the specification level, then you can do lots of analysis there. You can, for example, do data flow analysis. You can do various kind of you know, error checking to see if there are unused variables, clones. All of that can be done at the specification level. There's not a great deal of structural difference between the source and target. Usually, at least if they use structured code in the source, then the source and the target will have relatively same structure. So it should be possible to interpret results at the specification level to also understand them at the target level or source level. But I haven't done you know, any of that work, but in principle that you know, that could be done.
Yeah, one of the reasons I ask is the audience who writes the code that we transpile, they are not professional computer scientists. Mm-hmm. They're business users, typically working kind of the SQL database realm. You know, they're using Python and Spark. Well, they're using older legacy languages like SAS Institute language to do database analysis and analytic workloads. And because they are not professionals at writing really good code, some of the real world code falls into the category of either poorly written or anti-patterns. Mm-hmm. But as you pointed out, and many of our clients are in fact financial services institutions, like you mentioned. And so our role as implementers is to first determine what is the quality of the source code, to make sure that we do deliver accuracy against the source result, but also sometimes to interpret, were they actually doing, did they write the code they actually intended to write? Mm-hmm. And do we have to read their mind in the post hoc to reinterpret the code the way it should have been written? Anyway, it's more of an observation. I'm not asking for you to react to that, but I find the research level work that you and everybody else on this call are doing that I'm not worthy to even, I'm just somebody on the sidelines observing. But it's fascinating to see this level of work across these very common languages, because SAS Institute language is probably fading, you know, whereas Java, C, JavaScript are probably going to be around for a while.
Yeah. No, I've had the same. I've encountered the same kind of issues in financial code written in VB. So I'm going to show an example later on, which is from a package that's been used by lots of people, but it has various issues. For example, variables that are declared and never used, and all sorts of strange things, which of course can be detected and eliminated before you translate forward. Okay, there was another question, I think.
Yeah, there were other 3 questions.
Ah.
I think we opened the gates. There was one question in the chat from Dennis, one question from Michele, and before I saw also Sophia raises her hand. So maybe I think that the first one was from Dennis, written in the chat. And again, Professor, if we are taking too much time and if you want to go back to the slides, let us know. But I will start with
yes, maybe I'll just carry on a bit and then we can have some questions.
Perfect.
Yeah.
Okay.
Okay. So yes, coverage. So coverage and the functionality comparison. Yeah, notice I've only translated from C into languages which also have pointers, but even then, the semantics of pointers in these target languages it varies. So yeah, pointers are a bit of an issue. Nonetheless, we have quite good translation accuracy compared to some of these rule-based approaches like the Java to Python that you can get on the internet. And also compared to the machine learning approaches like transcoder. Now the related work, these approaches in the last few years have been machine learning approaches, learning implicit rules from generally large data sets of examples in source and target languages. And there's also these heuristic manually created translators. But for either of these, we have to repeat the translation construction for each pair of languages. Now, there's also been a number of MDE approaches that have done similar things, which perhaps best known are Modisco and Remix. However, these are focused on structural representation. So they take a big code base and they provide essentially a database of the information that's in those programs. What they don't do, as far as I can see, is do fine-grained semantic representation. There are also some transformation languages which can be used to do program abstraction. These are more traditional transformation language, model transformation languages, which are quite a lot more complicated than the text substitution language which we have in CSTL. Other people have also done bytecode abstraction and database schema abstraction. The contribution specifically from our approach is that we get a detailed semantic model. So for some of these financial applications, we can exactly model the calculations that they're doing. We can translate those from VB or from C. We can translate them into Python, and we get the same result, at least on the same computer, we get the same result. The CSTL defines the abstraction in a precise and explicit way. Those can be edited and changed as you need. So an end user can modify the translation as they want. And the other contribution, that's quite a big contribution, is that we've got a set of OCL library components that can be used not only for this translation, but also for defining new applications. Okay. The future work, which we're also working on, is to use some kind of symbolic machine learning to automate the construction of these abstraction mappings. So that's more blue sky work, but the idea is to remove some of this manual effort in constructing the abstractors. I would also like to give a demo. Is that possible, I wonder?
That would be great.
There's enough time.
Yeah.
Okay, let's see if I can. I think I better share my full
Audience tend to like demo very much, so I think everyone will be happy with that.
Yeah, let me see if I can share my whole screen here. Should be able to. Oh, yes. Okay. Yeah. Okay, so here's a source code. Here's a source code in Visual Basic, which is, as I said, taken from a large set of financial routines, which was doing bond calculation. But this is just a quick sort routine. Now, this is actually one of the cleaner bits of code in this set of libraries. But even this code has got an issue in that there's a unused variable here. So this C array, whatever it's supposed to be doing, we don't know, but it's not actually used in the code. It's merely passed through from one recursive call to the next. So this is the kind of error which could be detected at the specification level, and that variable then could be removed, that parameter could be removed when we forward translate. But otherwise, it seems to be okay. Now, I can call CSTL by itself on the command line. The first argument is the CSTL abstractor, and the second argument is the AST. The AST has been obtained from this program by using ANTLER Visual Basic 6 parser. The VBTUML is the abstraction script for Visual Basic, naturally enough. And again, there's a rule set for each grammar construction in the Visual Basic grammar. For example, constant statements declaring a constant just declares the constant with a suitable type, initializes it. Type translations, we can have type hints in Visual Basic with a suffix. These translate as OCL types, and so on and so on. So, it's a fairly systematic procedure to define such an abstractor. The person writing this obviously has to have a semantic model in their mind of what is the appropriate thing. So, the make directory statement, you can figure out that this is the make directory command of a file in the library, the OCL file library. Okay, so that's the script that's being executed. And okay, so I can run that script. I get various messages. The script is mainly a functional language. It maps an abstract syntax tree to text, but it can also include assertions during the execution. Typically, those assertions will declare types that some identifier is of a certain kind. So it's identified that the identifier array is actually a sequence, and so on and so on. It actually iterates through twice. That's why we get these messages twice here. You can iterate through the source as many times as you need to build up information. It's really rather like compilation. Now, this is a large, complicated bit of code. It's a recursive bit of code, so that's why this takes a little bit of time, but generally this is quite a fast procedure, the abstraction procedure. Yeah, second time round. Okay, it's just about finished, I think. There you go. So this is the OCL in a procedural version of OCL. And the main thing perhaps to notice is the data types have changed, so that the Visual Basic array has been recognized as a sequence of doubles. So this is now in an OCL type, a UML OCL type, which can be translated forward engineered to pretty much any language. Variants have become OCLNE, and so on and so on. Yeah, and you can see that there's quite a similarity between the source and the target in terms of structure. So a lot of the structural information has been retained, which helps debugging. Now, the translation to a language like Python can be done through the tool set like this. That again applies, it applies that the CSTL which we just seen. And it abstracts it to an OCL UML specification represented in the Agile UML toolset. The interest in Visual Basic is that it's often used to produce extra functionality in spreadsheets. So people write a spreadsheet, they write some custom functions in Visual Basic, which are then called from the spreadsheet. So this allows us to take that code and put it into UML. Here you can see the UML, couple of classes. I can do various checks here. I can do some type checking. I can do some various quality checks and so on. And most importantly, I can generate another language. Let's generate Python. That's pretty quick, as you can see. And I get my Visual Basic in Python. There you go. And yeah, I can run some tests, and basically it's a quick sort algorithm which works as expected. So as far as we can tell, the functionality has been preserved. Quick sort ascending, GG, this useless second parameter, and I think those are the bounds. You can do that. There you go.
Good, the full cycle.
So yeah, that's the kind of idea. Okay, any questions?
So before we start this, it's the first time we are doing this. We're doing this recording modality. So what we are going to do now is to stop the recording. So, and then we will proceed with the questions. So you will be free to ask questions that you are not proud of. Okay.